Now let's take a look at the parent functions for exponentials and logarithms. Let's take an exponential expression. That is, y equals some base to the x power. Now the base can be any number, but notice that our domain element, our x, is in the exponent, and our range element, our y, is by itself. Now here's the relationship between logarithms and exponents. We would say, using the same expression on the left, that log base b of y equals x. The advantage here is that the exponent itself is not playing an exponential role. It's just a regular number on the number line. So this is the advantage to logarithms, is they take the variables out of the exponents. They make it possible to deal with these variables when they're in exponents. Now, a very common one that we're going to start out with is y equals 2 to the x. Another really common one that you see, of course, is y equals e to the x, and that's going to correlate to our natural logs. So if I were to write y equals 2 to the x as a log expression, I would say log base. See how the base of our exponent is 2? The base of our log is going to be 2. Now, the interior of the log expression is going to be y, because a log equals an exponent, as in the logarithm is equal to, that whole expression is equal to whatever the exponent in your exponential expression was. Now for e to the x, we have this alternative notation, which is the natural log of y equals x. Alright, we're going to take a look at the graph for what we have written on the red line, and that is the y equals 2 to the x, and the log base 2 of a function, and that usually wouldn't be written with the y on the inside. But let's take a look at a short table of values. We're going to go -2 to 2. So we want to put these values in for x. 2 to the 0 power is 1, because anything to the 0 power is 1. And that makes a point that's going to be on our graph. Now, 2 to the -1, do you remember how to deal with negative exponents? It's going to be 1 divided by 2 to the first power. So 2 to the -2 is 1 divided by 2 squared, or 1 divided by 4. 2 to the first power is of course 2, and 2 to the second power is 4, which I can't fit on my graph. Now, I told you that logs and exponents are inverses, and this means that they reflect across the line y equals x. So you've graphed both of these before when we did our big collection of parent functions, but notice if we take every point and we reflect it across the x-axis, what we get is our log function. They're mirror images of each other. Here, where the red line is y equals 2 to the x, and the blue line would be the line log base 2 of x. All right, they are inverse functions to each other. All right, let's take a quick look at a few more expressions, and then we'll be done with this. So 2 cubed equals 8. That's the same as saying that the log base 2 of 8 equals 3. That means that the exponent that I would raise the base of 2 to get 8 is 3. These are the same expression. Let's try 2 to the x equals 7. Now here's the advantage to logs. I can't really guess what x would be, because all I know is that it's between 2 and 3. But if I write this as a log, I would say that the log base 2 of 7 equals my exponent, and this is very exciting because I take an impossible expression to work out, in a reasonable amount of time, and I turn it into something that I can calculate. Let's look at one more example using these log properties. Say you've got the log base 10 of 27, and it's equal to 3 times the log base 10 of x. Now, I know from my log properties that I can kind of package up what's on the right side and say that the log base 10 of 27 equals the log base 10 of x to the third. Now this works like a regular algebra function, Because I have the log of two things on either side, I know that those two things should be equal to each other. So 27 equals x cubed, and I can think, cubed root of 27? That's gotta be 3.